So today's topic is implicit differentiation. Now, does anybody know what the word implicit means? Like implicit versus explicit. What does the word implicit tell us? Like explicit is like openly, right? Something you're telling somebody explicitly what you're thinking about them or what you're doing. So explicit is openly. Implicit is closed. In mathematics, it means closed form. What do we mean by closed form? So for example, if I write an equation like this, x squared plus y squared equals to, let's say, 16. Does anybody recognize this as a special graph? What is this? A circle, right? And where is the center of the circle? At 0, 0. What is the radius of the circle? 4. This is an implicit equation. Why? Because typically in mathematics, we like to be able to write our equation like this. Y equals f of x. We like to know y explicitly as a function of x. But if you have something like this, x's and y's are all merged in, and you don't know what y is in terms of x, you have an implicit equation. The question is, what do you do when you have an implicit equation and say you want to find a slope around that circle at any given point x? Do you need, so we're trying to find dy dx here. Do you need to solve for y first before you can find dy dx? That's the question. Has anybody seen this before? Do we really need to solve for y first? The answer is no. You don't have to solve for y. There is a way to implicitly differentiate it. You keep it in a closed form. You differentiate it. That way, without even solving for y, you can actually determine what dy dx is. And that is our goal here, to learn implicit differentiation, where you don't even have to bother solving for y first. Let's take a look at a few examples. For example, derivative of x with respect to x is easy, right? We learned it on like day 2 of derivatives. What is that derivative? 2x. That's not implicit differentiation. That's regular differentiation. Okay, what if you're differentiating u squared with respect to x? This is kind of like the chain rule now. Right, you think of u being a function of x. So assume that u is a function of x. So what would the derivative be? 2u times u prime, or du dx, same thing. If I say u prime, you understand that to be du dx. Now, in this section, we're going to need to differentiate something like the following. Derivative of y squared with respect to x. Now, in that equation I just showed you, x squared plus y squared equals 16, we're not going to solve for y. But if you were to solve for y, would y be a function of x? If you were to solve for y in that equation. X squared plus y squared equals 16. If you solve for y here, y squared is 16 minus x squared, right? And y is plus or minus the square root of the right-hand side. So it is a function of x, right? So for most questions, we're not going to bother doing the solution and then differentiating. It takes very long time to do this. Instead, we're going to remember that y is a function of x, kind of like u. So what would be the derivative of y squared with respect to x then? 2y times y prime, or dy dx. What about the derivative of y cubed with respect to x? 3y squared times y prime, or you could also say times dy dx. Either one is acceptable. So when you are dealing with an expression containing y, and you're differentiating with respect to x, if this is the situation, basically you remember that you have to use a chain rule here, that y has an inside, y is a function of x. We may not know what it is right now, but just keep in mind that y is a function of x. But what if, back to basics again on the last one, what if you're differentiating x cubed with respect to x? What would that be? 3x squared, and if you like, you could say 3x squared times dx dx. That's the inside, derivative of the inside. But what is dx dx? That's 1. So we never bother putting that part down when you just have the x's. But when you have a y involved, we want to remember to multiply everything with the derivative of the inside, or dy dx. Now, keeping this in mind, let's take a look at that first example. I have a circle here with a radius of 1 unit. And we're going to find dy dx. And the nice thing about this method is you don't have to worry about solving for y first. You can directly start differentiating even when you have an implicit equation. Is this an implicit equation? Indeed it is. It's a closed form. You don't know why in terms of f of x, right? So this is an implicit equation, a closed form equation. So what we're going to do is differentiate both sides with respect to x. So this is the idea. Differentiate both sides with respect to x. And with respect to, I abbreviate as WRT, with respect to x. So starting with the first term on the left-hand side, what is the derivative of x squared with respect to x? 2x. What is the derivative of y squared with respect to x? Exactly. We've got to remember y is a function of x. It's 2y times y prime. And let us not forget to differentiate the right-hand side as well. Derivative of 1 is 0. Now, remember what we're trying to find. We're trying to find dy dx, right? That's y prime. So what we need to do right now is we need to solve this equation for which variable? Y prime, because that's what we're trying to determine. Okay, so let's solve for y prime. So first, I'm going to put the 2x on the other side. So y prime equals, divide both sides by 2y, right, to isolate y prime by itself. So now the 2's cancel, and I'm left with negative x over y. I say let's check this, just to see if it makes any sense for the circle. For example, right up here, what do I know about the slope of the circle right at that moment when x is, at this point, x is 0 and y is 1, right? What do I know about the slope at that point? This is a horizontal line. Slope should be 0, right? If you were to plug in the point 0, comma 1 in here, x is 0, y is 1, what would you get? Negative 0 over 1, which is indeed 0. The question didn't ask us to go this extra step. I'm going to put that like in brackets. This is like optional. I just did that to show you that this really makes sense. What we have found indeed represents the slope on the circle at any given point, x comma y. If they give you a point, you can plug the x and y coordinates in the answer to get your slope. I want you to notice something here. The answer has both x's and y's in it, and this is usually what's going to happen here. So in this section, they will usually give you both coordinates when they ask you for the slope, because you're going to need to plug in both the x and the y into the given equation, not just the x. Okay, let's do something a little bit more challenging. Let's do this one. For the last question?
On the right side, is it no?
The new question? It's 18 times x times y. That's what our right-hand side is. Are you asking how we're going to do that? Give me just a second. But the question is just 18xy. It's all multiplied. 18 times x times y. Okay, once again, we want to find dy dx. Now think about the alternative here. If you have to solve for y first, say you didn't know anything about implicit differentiation, this one would be a nightmare, right? There's a cubic equation here, trying to solve for y. It may not even be possible with basic algebraic techniques to do that. Luckily, we don't have to solve for y. We're going to differentiate right away both sides of the equation. Starting with the left-hand side, what is the derivative of x cubed? With respect to x, it is 3x squared. This is our solution. 3x squared plus the derivative of y cubed with respect to x is 3y squared times y prime, which is dy dx. Now, the right-hand side, we've got to be careful. I'm going to keep, this is like constant times a function. I'm going to keep the 18 down. Now, when I'm differentiating x times y, I need to be really careful. Remember, x is x, but y is a function of x. When you have the product of x and a function of x, which rule should you be applying to differentiate? Exactly, the product rule. So when you have x's and y's multiplied together, you need to apply the product rule to differentiate that. So let's begin. I'm going to write down the first expression as it is, which was x, times the derivative of y with respect to x, so that's dy dx, or y prime, plus, now write down the second factor, which is y, multiplied by what? Derivative of x with respect to x, which is 1. We're done with the differentiation process. We're supposed to solve for y prime, right? So I'm going to distribute my 18. And there are several y prime terms. So let's collect them on the same side. Everything else on the other side. That's how we're going to solve for y prime. Basically, the rest is algebra. We're done with the calculus. We're done with the differentiation. Okay, so let's go ahead and multiply the 18. Okay. Let's say I will collect my y prime expressions on the left-hand side. It really shouldn't make any difference either way you go. I'm going to collect them on the left-hand side. So I will keep 3y squared y prime there. Then I will subtract 18xy prime to send it over on this side. And on the right-hand side, what else should I have? Minus 3x squared. So everything with a y prime was sent to the left. Everything without a y prime was sent to the right. So now it's going to be easy to solve for y prime, right? What are we going to do to solve for y prime? Factor out the y prime and then divide both sides by its coefficient. So let's do that. So you might do it in one step. I'm going to do it in 2 steps. And then divide both sides by its coefficient. And we get the answer. But there's one extra thing we could do here. Like, could I cancel those 18s? No. Could I cancel the 3s? No, because they're parts of terms. There's a minus sign in the middle. We cannot do that. However, could we factor something from the top and the bottom and remove the common factors? Yes, and that factors 3, right? I can take out a 3 from the top, which is leaving us with 6y minus x squared, and take out a 3 from the bottom, which leaves us with y squared minus 6x. Now cancel the 3's, so we can leave our answer in the simplest form. Okay. I'll give you one now to work on, and then we'll come back and discuss it. Before we do so, any questions on this example? So the thing to be careful about is when you do implicit differentiation, be careful when you're differentiating something that has a y in it. You'll always end up with a y prime, basically. Also be careful if you have a product, you must always use a product rule, like x squared times y, anything, x sum to the power, y to the power multiplied, you got to use the product rule there. So let's do one more example. How about this one? And I'll give you a moment to think about it first. Okay. As I was going around the class, I saw most people had trouble with that middle term. So let's do that part really carefully, okay? So we're differentiating both sides with respect to x, right? What is the derivative of the first one? That's easy, right? 2x. Plus. Okay, I'm going to keep that 3 out for now. So I'm looking at the derivative of this quantity, x squared times y to the 4. X squared is my first factor, y to the 4 is my second factor. According to the product rule, I must write the first one. Again, you can switch the order of things, but you write one of them, and you multiply it by the derivative of the other, which is 4y cubed times y prime, because we're differentiating both sides with respect to x, right? Oops, I don't want to close the parentheses just yet. I'm not done with the product rule, right? Plus, according to the product rule, you write down the second expression as it is, and you multiply that with the derivative of the first. The derivative of x squared is 2x. Again, the product rule is something like this: uv prime plus vu prime. So we need two terms when you apply the product rule. Yes, George? No, you didn't have to keep the 3 on the side. Like, you could look at it, the first one as 3x squared, the second one is y to the 4. You could also do it that way. Absolutely. I'm going to distribute my 3 in the next step. Absolutely, you can do it that way. No, nothing wrong with that. Perfectly fine. How about the derivative of y cubed? 3y squared times y prime. And don't forget to differentiate the right-hand side, which should be 0. Now, I'm going to clean it up a little bit by distributing my 3. So 12x squared y cubed times y prime. When I distributed the 3 on the first term, and when I did it on the second term, I get 6x y to the 4. And then the last term is still there, 3y squared y prime. Now, my goal was to solve for dy dx, right? So I need to keep my y prime terms maybe on the left and put everything else on the other side. So I'm going to keep them on the left-hand side. And everything else goes on the right as subtraction. So negative 6x y to the 4 and negative 2x. And finally, factor out the y prime and then divide both sides by its coefficient. You know, at this point, I think I'm just going to do this in one step. Y prime will be whatever the right-hand side was. Divided by 12x squared y cubed. And what am I missing? Good. Just make sure everybody's following there. Plus 3y squared. If you prefer, you know, you could write one more step in there when you factor the y prime and then you do the division step. That would be fine too. Now it looks like we could do a little bit more simplification here. Actually, no, I'll take that back because there's a 6 and a 2 on the top. I thought maybe we could pull out a 3 from everything, but it looks like we can't do that. So we just are going to leave it like this. We cannot take out an x from everything. We cannot take out a y from everything. So we're just going to leave our answer like this. Yes? Because there was a multiplication there. When we distribute it, like everything here was multiplied, right? So you just have to multiply 3 times 4 there, which I put as 12, and the rest x squared, y cubed, y prime, they reappear here. But then there's a plus sign, so I distribute again on the other side after the plus sign, okay? Any other questions? All right, one more example. Okay, let's try this one. Okay, let's take a look. So differentiating both sides with respect to x, derivative of x is 1. Derivative of sine y with respect to x is first differentiate the outside function, leaving the inside the same. Then you multiply everything with the derivative of the inside, which is dy dx or y prime. And on the right-hand side, we need to apply the product rule, right? So x times y prime plus y times x prime. But x prime is really dx, that's 1. So we don't even need to bother putting that in there, really. I need to solve for y prime. So I'm going to get them on the left-hand side. So I have here cosine y times y prime minus x times y prime equals y minus 1. Factor out your y prime. And then, of course, to solve for y prime, divide both sides by that coefficient. Okay. Any questions about the solution? Did anybody get a little bit different version? Maybe something that looks like this. 1 minus y divided by x minus cosine y. Did anybody get that? Would this be correct answer also? Because the top and the bottom both have been multiplied by -1, right? So if instead of collecting my y prime on the left-hand side, if I was collecting them on the right-hand side, I might end up with something like this. So don't be alarmed. You're checking your answers from the book, and everything has been, if every single term has been multiplied by a -1, then you're fine, because basically they collected their terms on the other side. These two expressions are equivalent, so that's no problem there. Okay, one last one. Sorry, not that, this one. Okay, our good friends, logarithmic functions, right? We just learned about them, so let's include them in our discussion with implicit differentiation. ln of x times y plus y squared equals x plus 5. What is dy dx? You know, there are two ways to do this question, but I'm going to give you a hint. Let's all do it with the easier way. Okay, the easier way is to first simplify your ln. What is ln a times b? Plus ln b, right? If you write it out like that in your first step, it's going to be easier to take the derivatives. So that would be my suggestion. With the ln function, anytime you're differentiating a logarithmic function, think about, can I simplify it first? If you can do that, the answer will be much easier. All right. So I'm going to start by simplifying it first. Yes, there's more than one way to do it, but the easiest way is if you rewrite the ln function as ln x plus ln y. Then we can differentiate both sides with respect to x. Derivative of ln x is 1 over x. Derivative of ln y is 1 over y times y prime. Derivative of y squared is 2y prime. And on the right-hand side, derivative of x is 1. Derivative of 5 is 0, right? So now I want to solve for y prime. So I'll send the 1 over x on the other side. At the same time, let me also factor out the y prime from the remaining terms, okay? So 1 over x is going to appear on this side. There's already a 1 there. I'm going to subtract 1 over x, sending it there. And on the left-hand side, y prime times 1 over y plus what? 2y. So now all I have to do is divide both sides by the coefficient. So y prime is 1 minus 1 over x divided by this quantity. Now, technically, we're done. But it can't hurt to simplify this a little bit. Let's remember some of the ways we simplify what is called a complex fraction. You have fractions within a fraction. You can get common denominators. That would be one way. There's another way. If you multiply the top and the bottom by the least common denominator of all those little fractions, you can clear the whole thing. What would be the least common denominator for 1 over x and 1 over y? X times y would be a good common denominator. So multiply the top by x times y and the bottom by x times y. And if we do that in the next step, we should have no more denominators remaining in the top or the bottom. For example, this will be xy times 1. And if you multiply it with this, the x's cancel out. You have just a y. On the bottom, if you multiply it with this, the y's cancel, right? And the last term, multiply it with this now, 2xy squared. Again, I'm not going to do the details for the other method, but I just want to point out it was possible to do this question without splitting the ln in the beginning. But then you got to use the product rule, like 1 over u times u prime. U prime will call for the product rule, but everything else will be exactly the same. In the last step, once again, you will go ahead and find least common denominators.